A beetle gets swallowed alive by a toad. For 107 minutes, it sits inside the stomach. Acid covers its body. Muscle folds press it down. Digestion starts doing what digestion does. Then, the toad hears popping. The sound comes from inside its own gut. A Bombardier Beetle has fired boiling chemical artillery into the stomach wall, and the predator now has two choices: vomit or keep burning. This is the part that sounds like folklore. It is not. In controlled studies, 43% of swallowed Bombardier beetles force toads to throw them back up alive. The beetle crawls out covered in mucus, then it walks away. The question is not how a beetle survives a toad. The question is how an animal the size of a fingernail carries a 100-degree chemical explosion inside its own body without becoming the first casualty. There is no single Bombardier beetle. The name covers more than 500 species of ground beetles. They live across much of the world, absent only from Antarctica. Some move through temperate woods, some patrol grasslands, some work the wet agricultural fields of South Asia. In Punjab, Pakistan, one species, Pheropsophis catuare, walks through rice, cotton, wheat, and sugarcane fields at night. It measures about 10 to 18 millimeters long. Its head and chest shine reddish-brown. Its black wing covers carry yellow spots and bands, like warning paint on a machine too small to respect. Everything about it says beetle. Then something touches it. An ant bites the leg. A frog lunges. A spider closes in. The abdomen lifts. A pop snaps through the air. The attacker receives a jet of boiling, toxic chemicals moving about 10 meters per second. That is 22 miles per hour from an animal shorter than a paperclip. Scale that to a 6-foot human, and the body would spit boiling irritant at more than 1,000 miles per hour. The easy answer says the beetle stores acid. That answer fails. The beetle does not carry a ready-made tank of acid. It does not walk around full of burning liquid. The stored chemicals sit quietly in the abdomen as a clear water-based solution. Hydrogen peroxide. Hydroquinose. The first chemical appears in many living bodies. The second helps beetles make bitter defensive compounds and harden parts of their outer shell. Together, they sound dangerous. Together, in water, they can wait. No smoke, no blast, no tiny disaster. You would expect the weapon to begin in the storage tank. It does not. The weapon begins one chamber later. Deep in the rear of the abdomen, the beetle holds two gland systems. Each system has a storage sac, a duct, a valve, and a hardened reaction chamber. The storage sac keeps the ingredients calm. The reaction chamber makes them violent. When a predator attacks, muscles squeeze the storage sac. A valve opens. A tiny dose enters the chamber. The chamber walls carry enzymes, biological tools that speed chemical change. Catalase breaks hydrogen peroxide into water and oxygen. Peroxidase helps transform hydroquinones into benzoquinones, the chemicals that burn and irritate living tissue. The reaction releases heat, not because the chemicals hate each other, not because the beetle hides fire in its body, because the enzymes make a quiet mixture spend its energy all at once. In less than a millisecond, the liquid reaches 100 degrees Celsius. Water boils at that temperature. Inside the beetle, part of the mixture becomes steam. Steam expands. Pressure rises. The valve slams shut behind the blast. That closing matters. Without it, the explosion runs backward into the storage sac. The beetle cooks itself. The weapon becomes an autopsy. Pressure protects the animal from the pressure it creates. Then the chamber vents outward. Pop. A boiling spray leaves the rear of the body. For years, researchers could see the spray, hear the sound, and measure the chemistry. They still could not see the engine. The beetle's shell hid the machinery. So researchers used high-speed X-ray imaging. They filmed the abdomen at 2,000 frames per second. They expected a stream. They found a pulse engine. The chamber fills. The reaction flashes hot. The pressure shuts the valve. The chamber fires. Pressure drops. The valve opens again. More fluid enters. More heat. More steam. More spray. This cycle repeats 500 to 1,000 times per second. Open, burn, shut, fire. Open, burn, shut, fire. Open, burn, shut, fire. A World War II pulse jet engine used a similar rhythm. Human engineers built theirs from metal, fuel, valves, and war. Evolution built this one from soft tissue, hard cuticle, enzymes, and a beetle's rear end. That explains the blast. It does not explain the aim. A weapon pointed the wrong way only makes a confident mistake. Many bombardier beetles solve this with a flexible abdominal tip. The rear end acts like a turret. It can rotate about 270 degrees and send the spray backward, sideways, between the legs, or over the beetle's back. Hold one in your imagination. It stands on your palm. An ant bites the left front leg. The beetle does not flood the whole hand. It bends the abdomen and directs the chemical jet toward the contact point. The body turns a rear-facing opening into a targeting system. Some relatives use a stranger solution. Flanged bombardier beetles live among ants. In a narrow tunnel, turning around can cost time and limbs. Their spray exits backward, then catches curved plates along the body. The fluid bends around the curve. This effect has a name, the Coanda effect. It means a moving fluid can cling to a curved surface and follow it. Engineers use the same principle in aircraft and fluid devices. The beetle uses it to shoot forward from the rear. You would expect the nozzle to face the target. It does not. The body makes the shot turn a corner. This is where the weapon starts to look complete. Chemistry makes the heat. Steam makes the pressure. Valves make the rhythm. The abdomen makes the aim. Then, the grasshopper mouse walks in and ruins the whole myth. This small, carnivorous rodent hunts with a blunt solution. It grabs the beetle and shoves the rear end into dirt. The nozzle plugs. The boiling spray fires into mud. Steam bubbles harmlessly below the body. Then the mouse eats from the head down. The abdomen remains. A chemical cannon loses to soil. The toad uses another method. It swallows the beetle before the spray can solve the problem outside the body. The battlefield moves into the stomach. There, the beetle has no space. No light, no clean air, only acid and contracting tissue. If it has enough chemical reserve, it fires into the gut lining. Heat and benzekinones burn the soft inner wall. Gas expands. The toad's body rejects the meal. Shinji Sugiura tested this with Japanese common toads and bombardier beetles. Some beetles remained inside for more than an hour. One survived 107 minutes before the toad vomited it out. 43% came back alive. 43%. Not a rumor. Not a miracle. 43% of swallowed beetles turned digestion into a reversible mistake. The other 57% disappeared into the predator. That number changes the story. The bombardier beetle does not carry invincibility. It carries uncertainty. Predators do not face a guaranteed meal. They face a gamble with burns attached. Evolution does not need perfection. It rewards inconvenience. The cost begins before adulthood. A female lays eggs near mole cricket tunnels. The young larva that hatches does not look like a soft, helpless grub. It has long legs, a hard head, and jaws built for searching. It enters the soil. It must find the mole cricket egg chamber before its own energy runs out. If it fails, it starves. If it succeeds, it eats. Then the body changes shape. After the first meals, the larva sheds its skin and becomes shorter, wider, and less mobile. It no longer needs to run. It has found a room full of eggs. One larva can eat about 38.4 mole cricket eggs before it pupates. The decimal point matters. A researcher counted the remains closely enough to make the number refuse to become 38. Other bombardier beetles begin life with a darker arrangement. Some Brachynes larvae hunt the pupae of other beetles. The victim cannot escape. The larva bites into the soft body and drinks the blood-like fluid. As it grows, it attaches the host to its back. Then, it bends its own body backward through 180 degrees and keeps feeding. For about 48 hours, the host deflates. The adult chemical weapon begins as a child parasite wearing its food. This violence has a place in a larger system. In the irrigated fields of Punjab, mole crickets damage crop roots below the soil. Adult Phoropsophis beetles hunt at night. Their larvae attack the egg chambers underground. The farmer sees rice. The beetle sees a tunnel. The crop survives in part because small predators fight invisible wars beneath it. This also explains why the beetle became famous outside biology. Some people claimed the firing system could not evolve step by step. Their argument sounded simple. Half a chemical cannon should kill the animal. Half a pulse engine should help no one. The beetle's history answers without drama. Quinones already existed in beetle bodies. Hydrogen peroxide already appeared in metabolism. Storage pouches could make foul secretions before they made boiling spray. More enzyme activity could make the secretion hotter. Stronger chambers could hold more pressure. Better valves could protect the reservoir. A weak irritant still helps. A warm irritant helps more. A small pop helps more than silence. Natural selection does not need to invent the final machine in one move. It can keep any version that makes a predator pause, gag, drop, or remember. A pouch becomes a gland. A gland gains muscle. A chamber gains enzymes. A valve turns pressure into timing. A bad taste becomes a burst. A burst becomes artillery. Engineers care because the beetle solves several problems at once. It stores reactive ingredients safely. It mixes them only when needed. It creates heat fast. It vents pressure in pulses. It aims without electronics. Tiny machines struggle with all of that. The beetle does it with tissue. Not perfectly. Not safely every time. Not without cost. After 20 to 30 shots, the ammunition runs low. The body may need 24 to 36 hours to rebuild the chemicals. During that time, the animal still carries its shape, its warning colors, and whatever reputation the local predators have learned. A reputation can save a life. A depleted chamber cannot. That tension gives the animal its real shape. Not a tank. Not a superhero. Not a mistake in physics. A compromise. The beetle survives because it makes the world pay attention at the exact moment something tries to erase it. One chamber. One valve. 100 degrees. 1,000 pulses per second. One chamber. One valve. 100 degrees. 1,000 pulses per second. Every shot depends on timing. Too early, and the mixture wastes itself. Too late, and the predator closes its mouth. Too much pressure, and the chamber fails. Too little, and the attacker continues eating. The system works in the narrow space between chemistry and death. There is no victory speech in the soil afterward. The beetle walks under leaves. It joins other beetles beneath rocks. It mates. It carries parasites. Fungi can drill through its shell and tap its blood. Toads can still swallow it. Mice can still plug the gun. Nature did not build an animal that cannot die. It built an animal that makes death hesitate. There is another beetle that survives, forces no animal should survive. It does not fire chemicals. It does not burn predators. Researchers put it under the weight of a car, and its body did not crack. Its secret sits where two halves of shell meet.